Hi, welcome to this session. I will be talking about GCM and deterministic encryption. Deterministic encryption will come after I briefly go over the problems with randomized encryption, and then I will talk about a particular use case where deterministic encryption is of great value. Okay, let's get started first. This is the standard GCM that we have been talking for quite some time. I wanted to show you an interesting characteristics of GCM or randomized encryption in general. I have two plain texts that are same, as you can see, bunch of A's. Of course, you will never hard code secrets in the source code directly, but for proof of concept, more convenient for me to hard code the constants I would like to show you. So these two plain texts will be encrypted using GCM, and I wanted to show you how the ciphertext will look like for this particular scenario. So let me run this code. Let me just Java C GCM dot Java, should compile it first, and then Java GCM. Okay, so let me highlight some of the most important ones to start with. What you see here is that we have the first text AAA, right, bunch of A's, and the corresponding ciphertext together with IV and tags are shown here. For the next bunch of AAs, we have the corresponding IVs and ciphertext and the tags shown here. As we can see, they are very different from each other. They are not the same. Even though if we go here, our plain texts have the same values, the ciphertext look different. That's because of the dynamic or randomized aspect built inside this particular GCM cipher mode. What is the reason for that? The reason is simple. We basically call GCM and encrypt each plain text using a different IV. As you can see, I call GCM, but the IVs are randomly generated for each plain text. That means even though if two plain texts are the same, the resulting ciphertexts are different because of this randomized IV that we are using. Okay, I talked about in other sessions some problems if you don't use the random class properly, or if the random IV length is too small, this one. If you keep it small, you'll have collusion due to birthday attacks, so I'm not going to talk about this again. But for this particular session, the important thing is that if we have two plain texts that are same, no problems. As long as we use the random IV generation, we will get different ciphertexts. And an attacker cannot see whether the two ciphertexts correspond to the same plain text or different plain text. That's the so-called plain text CPA security, chosen plain text attack security kind of thing. Meaning, for given ciphertext, you can't deduce so much knowledge about the plain text. That's, informally speaking, that's what's happening here. Okay, this is good, but it's not always necessary. What if we argue that our plain texts are all different? Let's say we don't have the situation that the plain text will ever be same. For example, let's say you have a unique list of email addresses or social security numbers, then they are not going to repeat. So if there is some structure in the list of messages that we encrypt, then they will never have the same plain text. So it's okay to use a deterministic encryption scheme in that case, and I will explain to you why we need that in a moment. Consider this problem. Let's say you have a table made of million records, right? And you wanted to search whether a particular entry exists in the table. Maybe more simple example is what I'm going to show you now. Consider this example. I will explain what SIV means in a moment. Say we have a bunch of plain text, okay, like bunch of email addresses, and our goal is to find out whether a particular email address exists in the table, right? although this table is hard-coded here as a bunch of email addresses. In reality, you can imagine you have a database table, like a user registration table or something like that, and you have a bunch of email addresses. And the question is the given email address present in the table? How can we detect that? We can detect this by a couple of ways. One way is to, of course, go through each of the plain text after decrypting the table, and then see whether a given email address is present in the table or not. That may work very well for small tables, right? If you have only 10 email addresses or 20 email addresses and so on, you could quickly decrypt all of them and then match it up against the expected plain text and see whether it's present in the table or not. It's not a big deal. But what if your table has millions and millions of user accounts? Maybe you have a billion records, okay? And the column that uniquely identifies each record is the email address. Let's take it like that. The index to your table is basically the email address. In that case, it will be useful to think about deterministic encryption scheme. That's what I'm going to talk about now. So first, I will show you the basic idea, how the scheme works. And the core idea of the scheme is that we will not generate IVs randomly, but we will generate IVs in an interesting way. What I mean by interesting way is that we will use a key and call HMAC, okay? So let me explain this. How are we going to encrypt all of these plain texts using this SIV key? It's the regular encryption key. We will have an encryption key, of course, to encrypt our data. But there is something new called SIV key, synthetic IV key. What is this for? We will generate a key. That key will be used to derive an IV. So how are we going to do that? For example, we call the HMAC. This is my little HMAC wrapper. I will show you in a moment. HMAC, you can imagine as a MAC function, right? Which takes the key as input, the SIV key, and the plain text as another input. So in our case, each plain text is being passed to the HMAC function to obtain a unique IV. Okay, so here is your unique IV, and now the business is as usual. You call the regular encrypt function, which we talked about it several times. We pass the plain text and the encryption key and the IV. So from here onwards, there is nothing new, right? Everything is the same old GCM encryption model that I talked about several times. So what is new here is this part that I should work highlighting it. You have this new kind of key called SIV key, which is the name I invented, but basically SIV is a synthetic IV, and the key is used to derive the IV. That's why I call it SIV key. Maybe there's a better word for that. That doesn't matter. So we derive message-specific IV. Okay. What it means is that because HMAC behaves like a random function, if you have two messages that are slightly different from each other, let's say the first few characters are different, HMAC will completely give you a random looking IV. So you have your basic GCM requirement that each message is encrypted using a unique IV, otherwise you have a big problem. In GCM mode or in counter mode, the IVs should not repeat, all right? And that can be guaranteed by using a HMAC function. With very high probability, each message IV will be unique. And then it's just a regular function called encrypt and then decrypt or whatever. So what about the search problem? The search problem is now an interesting problem. So suppose I wanted to search whether my test.example.com is present in my database. How do I do that? First, during the encryption time, I encrypt each of my plain text records, right, based on the message. In this case, I'm only interested in the email column if you wanted to imagine like a database, okay? So I will encrypt it, and then I add it to my database, okay? See here, when I encrypt it, I get a ciphertext, right? And I just store that as a string. That this function does the conversion to string from byte array. And then I keep adding it to my ciphertext table. That's basically, I simulate it with a list, okay, list of strings. Okay, so what is the next thing I wanted to do? I want the user to be able to say, is test.example.com present in the database? So I will demonstrate that. How do I do that? So the idea here is interesting in that First, we will encrypt the string that we would like to search. So let's first go through this code. So we ask the user, give me some message that you would like to search for, okay? Then what we do, we derive the IV using the same SIV key that was used for IV generation purpose. Remember, SIV key is only used once. I'm sorry. The SIV keys are used for generating different IVs. The IVs themselves are unique. So let me repeat so make it clear. SIV keys are like encryption keys, but the only purpose is to generate a key that will be used as an input for IV generation, right? That's what you're doing. So we generated the SIV key only once here, right? And then we use that to generate IV. IV is supposed to be random. The HMAC will help us to do that. So I will show you the HMAC a little bit later. But once you have the SIV key, you are going to use the same encryption key, of course, to encrypt the message that you are looking for. Okay, for example, here is the input message. We will create an IV based on the input message. Why would this work? It will work because if the input message is present in the database, the IV that we will get here is the same IV that was generated when the data was encrypted at the very first place. Meaning, when the data was encrypted here, we need an IV, right? This IV, how did we get it? We got it from HMAC SHA-256 of the SIV key and the plain text. So if the plain text match what we have in the database, of course the data is present in the database. Otherwise, what will happen is that you will get some ciphertext that doesn't exist in the database. So now comes the searching part of the database. How do we do that? We just send to the database what we want to search. This is basically just the ciphertext we want to search. And then in my case, I'm simulating the database with a little simple array. I check in the list rather whether the ciphertext is present. If it is present, I say yes, the record exists. Otherwise, it doesn't exist. So let me summarize this. The first thing we do is we generate, of course, the encryption key to encrypt data, and then we generate an SIV key, the synthetic IV key. And the synthetic IV key, what is the purpose of that key? That key is used to derive message-specific IV. So every message will have a unique IV. Okay, that's the beauty. And we can now make the search much faster. Instead of decrypting all the million records in our database table, we will encrypt the data that we would like to search, and we will get the ciphertext, and then we do just a regular comparison against the database table. So the database itself is not aware of the fact that the data is encrypted or plain text or whatnot. So what this will work for all messages as long as the messages are unique, meaning that the table here, for example, here you see here first name, last name, blah, blah, blah. All of these must be unique. If you have two records that are the same, then it's not going to work. The reason why it's not going to work is that, say, test email is repeating 2 times, okay, in my table. Then what will happen? Then those ciphertext will be the same. Then you'll have the same ciphertext for the same plain text, right? Because the IVs are going to be the same. Of course, we are using the same key for encryption. Therefore, we will have the same ciphertext. So, which is not good in many cases. So as long as you can assure that all the messages are unique based on your message structure, deterministic encryption is a very good scheme to use. Okay. So let's just run it and see how it works for us. Now I will just write GCM. So the program is encrypting all of the list elements that we put in our plain text list. And now it's asking, do you want to search for something? Let's say whether we can search for test.example.com, which we know exists in our database. Okay, it says it exists. So what about something that doesn't exist? Let's just type something. Okay, error message, it's not in the database. Okay, what is the benefit of this approach? The benefit of this approach is that we don't decrypt each and every ciphertext to match against the plain text that we would like to search for. Instead, we take the plain text, we encrypt the plain text. Of course, in order to encrypt, we need an IV. To generate an IV, we use the message itself. So we compute HMAC of the message using so-called SIV key. That will give us IV. Therefore, we will get exactly the same ciphertext that is produced during the encryption at the very first place. Therefore, we can do simple comparison of our ciphertext against the ciphertext stored in the database. Okay. So to sum up, I can just write it from an algorithmic perspective. Step one is basically you encrypt your data. Say, example, list of emails, or social security number, something unique, right? This must be the prerequisite, of course. Okay. Then you of course need an IV to do that. So let me clarify that first. In order to encrypt your data, you need to generate. So step 0 is generate data encryption key. Data encryption key. People call it DEC. Okay. Also generate an SIV key. Okay. So these two things are done usually only once. For very, very long time, you can use those two. And now, sort of for each message in your list of messages, what are you going to do? Compute HMAC. Okay. So let me write it like algorithm. Compute HMAC of what? HMAC requires a key, right? So we pass the SIV key and your message. Okay. So we do this for every message. So now we passed this. What will HMAC return? HMAC will return. So this becomes an IV for us. Okay. Now we are ready to encrypt the data. How do we do that? We just call our encrypt function to get the ciphertext, right? Ciphertext is nothing but encrypt of. We need the DEC. Of course, the DEC is the one that will do the data encryption and the message and the IV, right? So these three things go into the encrypt function. It will produce the ciphertext. And then there's no reason for semicolon. We store the ciphertext in a database table, right? Ciphertext in a DB table. Okay, so this is basically how the data is encrypted. Now, let me explain how the search will work. In order to do the search, you ask the user, give me the search string, right? Okay, let's call it search string. Okay, now we will do the same. We will compute HMAC. So let me call it test IV. Is HMAC of SIV key followed by the search string, which will give us the test IV. And now we have to also encrypt the string that we would like to search for, right? Let me call it test ciphertext is equal to encrypt of, you have to use the same key, of course, the DEC. And then what else we need? The search string, right? And the IV. What is the IV? Test IV. Okay. All right. Usually we put key and IV one after another, but it doesn't matter in this case. I just quickly typed it. So we have the test ciphertext. Now the search algorithm is check whether test ciphertext is stored in the DB table. So if there is a record that has if present, if as the data, the search string is in our DB. Okay, otherwise it's not. Okay, so why would this work always? It will work as long as the messages are unique. So let me repeat this very carefully, please. Warning, as long as the messages are unique, like for example, a primary key or an index or something like that, then this deterministic scheme is secure. Also, you have to make sure that you're using two different keys. One key for the data encryption, right? The DEC key. Other is the SIV generation key, right? The SIV's IV generation key rather. So the IVs are obtained using HMAC, which would also require another key that I call SIV key. Okay, these are the two different keys that you need. That's the reason I said here in step 0, generate DEC and generate an SIV key. So the benefit is simple, right? We don't decrypt all the million records. We just encrypt over here what we want to search, and then we compare the ciphertext against the ciphertext stored in the database table. That's why this thing works perfectly. All right, let me show you my HMAC, which is very easy. You can find it online in Java documentation and things like that. So HMAC takes the secret key and a message is input. It instantiates the MAC object, and then it does some basic template code here, and then it performs the actual MAC calculation. Okay, so this is what I called from my other code, right? Which will generate a unique IV for each message. This is the property of HMAC. HMAC behaves like a PRF, so-called the pseudo-random function. Okay. All right. As long as we can be sure that our messages are unique, this is a good scheme to use. Deterministic IV is a good scheme to use. Okay, synthetic IV, deterministic encryption scheme using synthetic IV. Okay, one final remark is that if you look at my implementation here, the IV length is not even declared because the IVs are now produced using HMAC, and HMAC 256 SHA algorithm produces 256 bits of data, which is 32 bytes. 32 bytes of data become our IV, which is perfectly fine for GCM mode. GCM mode happily accepts 32 byte IV, so we have no problems to use HMAC like the way I did it today. All right, that's all. Thank you very much.